Okay, so welcome back, everybody. I wanted to get into the specifics from yesterday of computing uh, uh, general solutions to homogeneous second order specifically, but we'll see quickly how that applies to higher order equations, constant coefficient differential equations. So yesterday, if you remember, I defined the characteristic polynomial for an equation like this. So again, this is an nth order linear constant coefficient homogeneous equation. The characteristic polynomial is defined to be this. So basically, it's a polynomial in Z where the powers of Z at each term are determined by the order of the derivative in each of these terms. The coefficients, these constant coefficients, determine the coefficients in this polynomial, okay, in the same way. So quick examples, the thing we were doing, the example we used several times yesterday. This second order equation has characteristic polynomial, z squared plus 2z plus 1. Okay. And I asked the question, like, why? What does the characteristic polynomial have to do with anything? And my answer is that constructing a fundamental solution set, that is a solution set from which I can build the general solution, that is, I could say general solution is, linear combination of those fundamental solutions. This comes directly from the characteristic polynomial. So let's see how this works in the case n is equal to 2. So second order case. Okay. So what does my general second order equation look like? Let's say that I've already divided through by the leading coefficient. So this is always a monic polynomial, that is a polynomial with leading coefficient 1. So let's say that this is what I'm looking at. Something like that. Okay. Well then, in this case, my characteristic polynomial should be what? Its p of z is z squared plus a1z plus a naught. Okay, well, writing it like that really doesn't do me any good, because if I want to actually get at what's going on, I need to see what happens in each case. The point, though, to stress is that this is always a quadratic. Always a quadratic in the n equals 2 case. N here referring to the order of the differential equation. So for a second order equation, this is always a quadratic. For a third order equation, this would always be a cubic polynomial. For a fourth order equation, it would be a quartic or fourth degree polynomial, and so on. And this is just because of this fact that the degree of the characteristic polynomial is n, which is the order of this differential equation. Okay, so if the differential equation has a nth derivative of y term, then the highest order term showing up in the characteristic polynomial is this z to the n. Okay. All right. So this is always a quadratic, which means that I can always find the roots, right? Using the quadratic formula if needed. Of course, many times it's easier than that because the thing is factorable, right? The idea, I can always immediately find the roots of a quadratic. So I can always immediately have the roots once I have the quadratic polynomial in front of me. Right, so there's never anything else that I necessarily have to do, right? I could always just use the quadratic formula here. All right, and I've claimed that the roots of this polynomial have something to do with the general solution of this differential equation. So let's see how this works. So let's do an example here. Let me just cook something up really quickly. Let's see here. Yeah, so let's do something like this. Okay. So y double prime plus 5y prime plus 6y is equal to 0. Okay. All right. So the characteristic polynomial is z squared plus 5z plus 6. Now I could plug these things into the quadratic formula just fine and find my roots. Or I can notice that, oh, this thing actually factors pretty quickly. So this is z plus 2, z plus 3. You can just check quickly that that is indeed how that factors. So this is z plus 2, z plus 3. Okay. All right. So now what? Well, what are my roots, right? So my roots of this characteristic polynomial, I'm setting this thing equal to 0, asking where this thing is 0, clearly at minus 2 and minus 3. Okay. How does that help me? Well, let's do a little aside for a second. Okay, so here's my aside. What are the possible cases for a quadratic polynomial? Right? What are the possible cases for how its roots can be configured? Well, remember, right? If I have a quadratic, there's 3 possible ways that it can be configured in the plane. We'll assume that it's monic so that it, opens up. Of course, the picture opening down is pretty much the same. So, the point is, a quadratic polynomial, what does it look like? It looks like this, or it looks like this, or it looks like this. One of those 3, right? Those are the only 3. Well, what are these cases? In this case, it crosses the x-axis twice. There's my roots. So those are 2 real roots, right? Here, in this case, it only touches the x-axis. So in this case, I have 1 real double root. We will see later on, like algebraically, it makes a lot of sense to treat this as 2 roots, even if it's the same number, which is why we use the terminology double root. It's a double root, or a root of multiplicity 2. We'll see how that becomes important later. But, so we would call this a double root. So if this root happens at 1, if we're listing out the roots, we might list 1 twice. Okay. All right. And then in this case, it doesn't cross the x-axis at all. So it has no real roots. But this is the case of 2 complex roots in a conjugate pair. Now, I'm going to go over some algebraic facts that you might have forgotten about roots of polynomials. One of them that you're going to hear me say a lot is that when you have a polynomial that has real coefficients, so all the coefficients are real numbers, that's exactly the case we're going to be in this course all the time. So all these a sub i's are going to be real numbers. If you're in that case, okay, then the polynomial that has real coefficients, if you ask what kind of roots it can have, well, it can have, it can have any sort of root. It can have real or complex roots. But any complex roots that it has have to come in conjugate pairs. So it's not allowed to have a single complex root without having that thing's conjugate. So I'll talk a little bit more about that if you're confused by what it means when I say complex conjugate. We'll talk about this stuff more later. But let's just quickly review the cases, right? So for second order equations, okay, there are three cases. There's case 1, two real roots, two distinct real roots. So let's call those real roots R1 and R2. And we'll say R1 is not equal to R2. That's what the word distinct means. So these are two real roots in the sense that these are two different numbers. Now we're, contrasting that with a situation where we would have a real root that's a double root, so it's actually the same number, but we're counting it twice. Okay. So two distinct real roots. So that's exactly the case we're in here. Okay, so let's see what to do in this case. So in this case, a fundamental solution set is given by e to the r1t and e to the r2t. Another way of writing that is to say y1 of t is e to the r1t and y2 of t is e to the r2t. Okay. If r1 and r2 are distinct, these two are linearly independent. So that's why I'm calling it a fundamental solution set. So you can check for yourself that if r1 and r2 are different, these are linearly independent. I can compute the Wronskian and see that these are linearly independent. The other thing to say is that they are actually solutions to this, so long as these are the roots of the characteristic polynomial. Okay, so in this case, a fundamental solution set is given by these two, and thus the general solution is given by y of t is c1 y1 of t plus c2 y2 of t, which, rewriting it, this is c1 e to the r1 of t plus c2 e to the r2 of t. Okay. All right. So let's see, first of all, that this actually works in our example, and then we'll return to this. Okay. So here's our example. All right, let's continue on from here. So I have two roots. They're definitely distinct real roots, so I'm in the case where I can use this. So then my fundamental solution set should be y1 of t, which is e to the minus 2t, and y2 of t, which should be e to the minus 3t. Now, as I already told you yesterday, it turns out that this process that we're doing is always going to yield a fundamental solution set. So if you believe that, then you don't need to check that these things are actually linearly independent, but I just want to check for our sake to make sure that they are. So first of all, before I can check that they're linearly independent, both of these should solve this thing. Okay, so let's check that both of them do. So what is y1 double prime, or here I'll start out with y1 prime. So y1 prime is minus 2 e to the minus 2t. y1 double prime is 4 e to the minus 2t. Okay, and so y1 double prime plus 5 y1 prime plus 6 y1 is equal to 4e to the minus 2t plus 5 times y1 prime, which is minus 2 e to the minus 2t, plus 6 times y1, which is e to the minus 2t. So I get 10 e to the minus 2t minus 10 e to the minus 2t. So 0. Okay. You can similarly check for y2 that this thing solves the differential equation. And so it makes sense. So these are both solutions. So it makes sense to compute their Wronskian. So what's the Wronskian of y1, y2 here? Well, this is y1, y2 prime minus y2, y1 prime. Okay, y1 is e to the minus 2, so this is, or sorry, e to the minus 2t, so this is e to the minus 2t. y2 prime is minus 3 e to the minus 3t. Okay, minus y2, which is e to the minus 3t, times y1 prime, which is minus 2 e to the minus 2t. And this is equal to minus 3 e to the minus 5t. Minus minus, this is plus 2 e to the minus 5t. So this is minus e to the minus 5t. And this thing is always negative, right? It's never 0. So the Wronskian is never 0 for this thing. So this is, in fact, a fundamental solution set. And thus, a general solution to our original equation. Let me just bring it back real quick. So a general solution to y double prime plus 5y prime plus 6y is equal to 0 is given by exactly what I did yesterday with the fundamental solution set. It's y of t is arbitrary constant c1 times y1 plus arbitrary constant c2 times y2, which is, in this case, c1 e to the minus 2t plus c2 e to the minus 3t. So there it is. Okay. All right, so a couple of things here. First of all, I have two constants here, right, that are my arbitrary constants determining this. So the question is, so a quick question about IVPs. Let's go back to this example. Let's say that my equation is y double prime plus 5y prime plus 6y is equal to 0. And I have some initial condition. So y of 0 is equal to, say, 3. Okay. All right. So y of 0 is equal to 3. Is this going to be enough to actually determine which member of this infinite family, parameterized by these two constants, I actually have? Well, if you think about it for a second, if you impose this initial condition, say here, let's just do it really quickly. So if I impose the initial condition y of 0 is equal to 3, what would I get here? I would get 3 is equal to y of 0, which is equal to, if I put 0 in here, that's 1. If I put 0 in here, that's 1. So that's C1 plus C2. So I would have a single equation, and all I would be told is C1 plus C2 is equal to 3. But how many C1 and C2 satisfy that equation? Well, infinitely many, right? This is an equation that it's a single equation, but there's two unknowns. So I would have a choice here, right? So C1 and C2 could be very many different things, right? C1 could be 1/2, and so, you know, C1 could be 1/2, and this could be 2.5, right? C1 could be 1 and C2 could be 2. C1 could be 2 and C2 could be 1, right? So there's a lot of choices here, but that's not what I should get out of this process. So in fact, even though right now I've only talked about existence and uniqueness for first order equations, there is an analogous existence and uniqueness theorem for these higher order equations. And existence and uniqueness should tell me that for this IVP, for a properly given IVP, I should be able to pick out a unique member of this family. I should be able to pick out a unique thing in this general solution that satisfies the IVP. So it's not enough to specify a value on the function itself. I must also specify a value of its derivative at some initial point, at the same initial point. Now, a quick kind of generalization after we do this. Well, I'll get to it here in a second. So how does this work then? So I need to take the derivative of y, so y prime of t, in this case, just from here, is minus 2c1 e to the minus 2t minus 3c2 e to the minus 3t. Okay. And so I impose both of these conditions. So 3 is equal to y of 0, and y of 0, as we saw, is just c1 plus c2. And 5 is equal to y prime of 0, and y prime of 0 is minus 2 c1 minus 3 c2. So in the first order case, to impose an initial condition was to solve a single equation for a single unknown, a single arbitrary constant. So then imposing a set of initial conditions is going to be solving a system of equations in that many unknowns. So for instance, 2 equations here and 2 unknowns. Okay. So how do we do this, right? There's a number of ways to do this. So one is I could, so you know, then here I'm getting into the world of linear algebra, solving these. Of course, the bigger and bigger the system, the more linear algebra stuff you'd probably find it convenient to use. Here, because it's just 2 equations and 2 unknowns, quickly, what can I do? I can multiply the first equation by 2 and add it to the second equation. That way my C1 cancels out. So if I do that, what do I get? So 2 times first equation plus second equation. So this is 2 times 3 is 6 plus 5 is 11. So this leads me to 11 is equal to 2. C1 plus minus 2C2 is 0. Plus 2C2 minus 3C2 is minus C2. So minus C2 is 11, which means that C2 is minus 11. And if C2 is minus 11, then I can use the first equation. For instance, C2 is minus 11, then C1 has to be 14, right? And so the unique solution satisfying this IVP is y of t. So this implies that C1 is 14. So then the unique solution satisfying this IVP would be 14 e to the minus 2t plus 11 e to the minus 3t. Minus 11. Minus 11. There we go. Okay. So that's how this would work out. So this is how dealing with IVPs for a higher order equation works. Now a quick question or a quick statement maybe about generalization. So if I have an IVP that's an nth order thing, right? So it looks like this. We could state this, of course, for a more general equation, but right now I'm just going to keep it with homogeneous equations. If I have an IVP like this, then it's not enough to have a condition, or maybe I'll call this an initial t. It's not enough to have y of t sub I is equal to, y sub I here. And you could call this like y naught, if you like. What's the best notation for this? Maybe here's what I'm gonna say. So I'm gonna call y of t sub I y naught, and we need y prime of t sub I, and we'll call it y sub 1, and y double prime of t sub I we'll call y sub 2. This is how the textbook does it. And so on. How many of these do I need? For an nth order IVP, I need n minus 1, right? So going back here, it was a second order equation. So I needed conditions on the function itself and its first derivative, right? Its second minus 1 derivative. So up to n minus 1 derivatives is how many I need. So the n minus first derivative of y at this, we'll call it y sub n minus 1. Okay. So then this gives me n total conditions. So if you have an nth order equation, I need n initial conditions, okay, for that thing to be nicely determinable, okay, from the initial conditions, like always. Okay. So now what? So I had this, I was trying to understand what was going on by cases. So for second order equations, I had the first case where we had two distinct real roots. Well, what's the second possibility? So the second possibility is one real double root. We actually did an example of an equation like this yesterday. Okay, this is one of our examples that we used. One real double root, we'll call it r sub 1. Okay, I'll revisit that example that I did yesterday here in a second. In this case, a fundamental solution set is given by y1 of t is equal to e to the r1 of t, so just like up here. But now we saw what happened yesterday. This y2 of t, I can't do another e to the r1 of t because that won't be linearly independent with this. It's Wronskian, it'll be 0. So what I do is t e to the r1 t. This is the idea. So this is a fundamental solution set, which implies a general solution is given as y of t is c1y1 plus c2y2, as always. But this is equal to c1 e to the r1 of t, so that term looks the same as above, plus c2 t e to the r1 of t. Right? Notice there is no r2 here. There's only a single real double root. Up here, the reason why we didn't run into issues with linear independence was because r1 and r2 were different. Right? That is why when we computed this Wronskian, we were happy. That thing was always non-zero. Here, I can't just copy e to the r1 of t here because these two things are the same. The Wronskian will definitely be 0. But throwing in this t factor does it. And it turns out that throwing in this t factor will also have this as a solution. So if this thing solves an equation with one real double root, then so will this thing. So both of these will be solutions, and there'll be a fundamental solution. So a fundamental solution set, so their Wronskian will be non-zero. Okay, so a general solution is this. Okay. Let's go back to that example from yesterday. So if you compare this to yesterday, this is where I was getting that solution from. So our easy example from yesterday, y double prime plus 2y prime plus y is equal to 0. What's its characteristic polynomial? Well, its characteristic polynomial is p of z, which is z squared plus 2z plus 1, which I notice factors immediately as z plus 1 squared. So what are the roots? Well, the roots are z equals minus 1 and minus 1, right? It's one real double root. I'm listing it twice here. Okay. All right. So roots are minus 1 and minus 1. All right, so then what does this yield from this case I described here? In the case of one real double root, my fundamental solution set is e to the root times t and t e to the root times t. And then a general solution is a linear combination of those things. Okay, so then what's my fundamental solution set? So y1 of t is e to the minus t, and I'm claiming y2 of t is t e to the minus t. So that my general solution, right, that any solution must be of the form of, is y of t, which is c1 y1 plus c2 y2, so that's c1 e to the minus t plus c2 t e to the minus t. So I'm claiming any solution to this equation has to be of this form. Okay, we actually already computed the Wronskian of this thing yesterday. And we also already showed that it actually solves this differential equation yesterday. Okay, so this is what we get. Okay. All right. Now returning to this page. We're talking about second order equations. Right? What are the possibilities? You can have two distinct real roots, so we've taken care of that. You can have one real double root. We've taken care of that. For a quadratic polynomial, there's only 3 total cases. Right? 2 distinct real roots. That's case 1. One real double root. That's case 2. And the last case is 2 complex roots in a conjugate pair. Okay, so case 3. 2 complex roots that we could write as, so z is equal to lambda plus or minus mu I. Okay. All right. So this is what is meant by a conjugate pair. Okay, so a quick aside, because this will become important later. If z is a complex number, we'll say it looks like lambda plus mu I. Okay, then z bar, which is lambda minus mu I, this is the complex conjugate of z. Okay. So when I say that a pair of roots come in a conjugate pair, what that means is that they look exactly like this. So there's the root lambda plus mu I, and its conjugate lambda minus mu I. Okay, that's what I mean. All right, so this is the only way that these can show up in these equations, and this has to do with the fact that the coefficients in these equations are real. So this puts a restriction on how the complex roots can show up. Okay, so anyway, in this case, all the complex roots have to show up in a conjugate pair. That's going to be true for any order equation, but it's possible for higher order equations, of course, you could have more of them. For a quadratic, I only have 2's. Now, here's where I'm going to invoke this, and we'll talk about this a little bit more later when it becomes more important. But there's the fundamental theorem of algebra, which you may have heard in some form before, which is that how many roots does an nth degree polynomial have? Right? How many roots does an nth degree polynomial have? Let's do another aside here quickly. How many roots does some degree n polynomial have? Notice I'm asking how many roots, not how many real roots, just how many roots. The answer, by, you can call this fundamental theorem of algebra if you like the answer, counting with multiplicity, it always has n roots. Exactly n. Okay, so for a second order equation, let's just go through our cases. I can have two distinct real roots. Well, there clearly I have two. One real double root. What I mean by counting with multiplicity here is that we talk about the multiplicity of the root, which in this case is 2 for a double root. We'll talk a little bit more specifically about what we mean by multiplicity when we get to non-homogeneous equations, because we'll definitely need to understand it. Okay, but for a quadratic, the highest multiplicity you can have is 2. Okay, so this is a double root showing up in this way. So I have a double root, which I count twice. So even though it's a single real number, it counts as 2 roots. So that's what I mean by counting with multiplicity. And then in the last case, I have 2 complex roots. Remember, I did not specify whether I was talking about real or complex here. I was happy with either. And so the answer is 2 for a quadratic. So that makes sense, right? That like going forward, higher and higher order, this counting with multiplicity business lets me say that, oh, this always has exactly n roots. So I know exactly how many roots to expect from a characteristic polynomial. Okay. And so this also tells me that this is the exhaustive case. This together with the fact that these complex roots have to come in a conjugate pair. So this is it. This is the last case. All right. So in this case, my two, so in this case, a fundamental solution set is given by e to the lambda t times cosine of mu t. Okay, and e to the lambda t times sine of mu t. Okay. All right. And so thus, so this is my y1. This is my y2. Thus, a general solution is given by y of t is c1 e to the lambda t cosine mu t plus c2 e to the lambda t sine mu t. Okay. Okay. So let's do a quick example of this. Let me think for a second. Yeah, so let's do something like this. Let's do y double prime plus 2y prime plus 2y is equal to 0. Okay. So what's the characteristic polynomial? Well, this is z squared plus 2z plus 2. I can plug that into the quadratic formula and totally get these roots. Or I can just notice, hey, wait, this is actually really close to a perfect square here. So this is a z plus 1 squared plus 1. All right, that's the thing to notice, right? This is z squared plus 2z plus 1, if you like. So then setting this thing equal to 0, right? So at roots of this thing, z plus 1 squared plus 1 is equal to 0. What does that mean? That means that z plus 1 squared is equal to minus 1. Taking the square root of both sides, of course, square root of minus 1 is I. Right, so this is z plus 1 is equal to plus or minus I. Right, and z is equal to minus 1 plus or minus I. Now, you would have gotten this exact same thing if you had used quadratic formula, so you definitely don't have to do it this way. But I'll go ahead and tell you that for the most part in this class, you will be able to do most of these problems like this. So if you want to save yourself from having to apply quadratic formula and go through all that, then you can usually just get at it from the algebra here. Okay. Oh, this should be a t. This should be a t. Sorry about that. I see that now. No, this should be a t. I think I said t when I was writing it, but for whatever reason I wrote I there. This should be that should be a t. So yeah. Okay. So here are my roots. Then this gives rise to general solution from this. Thus, general solution is y of t is equal to c1 e to the lambda. Lambda is minus 1 here, so this is c1 e to the minus t times cosine of mu t. Mu is 1. So this is c1 e to the minus t cosine t plus c2 e to the minus t sine t. So there it is. You can check on your own if you want to see whether or not this thing actually is a solution, or you could individually check each term to make sure it's a solution. Either of those you can do to convince yourself. But now I think we've seen enough evidence to say one. So in fact, if I follow this process, I am guaranteed to get a fundamental solution set. So I typically do not need to check this. So I typically don't need to check this by computing the Wronskian. Now, I could ask you to compute the Wronskian. So I could ask you to compute the Wronskian to actually verify, but this is just telling you that it's a fact that if you follow this process, you're going to end up with linearly independent solutions or a fundamental solution set. So you actually don't need to check the Wronskian typically, because that aspect of it is guaranteed. Okay. All right. So let's do a few more examples. So now we have, maybe I should write it all on this page. Now we have exhausted all cases. Right? So if when n is equal to 2, what are the cases, right? Case 1, two real roots, R1, R2. So, of course, when we're talking about roots here, we're talking about the characteristic polynomial. So the first step in any of these problems is to write out the characteristic polynomial and then find its roots and see what case you're in, right? So case 1, 2 real roots, R1, R2. This implies general solution is C1 e to the R1t plus C2 e to the R2t. Okay. Case 2, one real double root, and that's, we'll call that R1, since it's the only one. This implies general solution is y of t, which is C1 e to the R1t plus C2 t e to the R1t. Okay, and case 3, complex roots in conjugate pair. So lambda plus minus I mu. So this is telling us that the general solution is y of t is C1 e to the lambda t cosine of mu t plus C2 e to the lambda t sine of mu t. Okay. So these are my 3 cases. So what is the process? So step 1, write out characteristic polynomial and find its roots. Step 2, figure out which case you're in. And then you're done, right? It's one of these 3. So it's either this one, or this one, or this one. Now we'll see eventually, and by eventually, probably by the end of tomorrow's lecture, maybe. If not, then we'll finish it on Monday. But we'll see very soon that actually this process is pretty nicely generalizable to the higher order case, where this process is more or less the same for third order, fifth order, or whatever order equation. The only thing that is tougher in that case is actually finding the roots. That's it. But assuming that you were given the roots, right, this process is actually just as easy in the higher order case. And you will be given explicitly examples where you have higher order equations, and I'll either give you the roots, or it will be easy for you to find the roots, and then from that you'll have to construct the general solution, even to like an order 12 equation or something like that. So this is something that's actually pretty easy, and that's exactly what I meant when I said that it turns out that if you understand how to do second order linear stuff, then you actually know how to do higher order linear stuff. It's not that much more complicated. It's actually the same process. Okay. All right, so there it is. Let's do some examples. So this is very, very important for you to practice because you are going to do this over and over and over again. So let's do a bunch of examples. Because as I said, you are going to do this over and over and over again. All right, so here. So let's solve the IVP, which is, let's do something like, let me think here. Let's do y double prime, maybe minus 6y prime plus 9 y is equal to 0 with initial conditions y of 0 is equal to 2 and y prime of 0 is equal to 4. Okay. All right. So again, what is the first step? I see this equation. It is homogeneous because the right-hand side 0. It's a constant coefficient. Second order. So I can apply all these things that we've been talking about. All right, so if any of those fails, right, then technically I don't know what to do. So if this right-hand side is not 0, if these coefficients are not constant, then I don't know what to do here. All right, but I'm in good shape. So characteristic polynomial, what is that? So p of z is equal to z squared minus 6z plus 9. Okay. All right, well, how does this factor? Does it factor? Yeah, so this factors as z minus 3 squared. So what are my roots? I have one real double root. So I have one real double root. That's z equals 3. All right. So then this tells me immediately what the general solution is. So the general solution is y of t is c1e to the 3t plus c2t e to the 3t. So there's the general solution, but I was told to solve the IVP, right? So I need to impose these initial conditions to find the unique solution that I should be guaranteed to this equation. Okay, so let's quickly compute y prime here. So what is y prime of t? So this is 3c1e to the 3t plus c2e to the 3t plus 3c2t to the 3t. So that's y prime of t, right? I have to use the product rule on this term. Okay, and so let's impose these initial conditions. So 2 is equal to y of 0. Y of 0 here is going to be, so here I would get c1 times e to the 0 plus c2 times 0 e to the 0. So actually, here I just get c1. Well, that's easy enough. What about the second equation, right? So this first equation is not going to be able to tell me anything about c2 because c2 is multiplying 0 here. So then this second equation, 4 is equal to y prime of 0. Y prime of 0 I can get from here. So this is 3c1 e to the 0 plus c2 e to the 0 plus 3c2 times 0 e to the 0. So again, this term goes away, and I'm left with 3c1 plus c2. But I've already seen that from the first thing, c1 is equal to 2. So I have 4 is equal to 3c1 plus c2. c1 is equal to 2, however, so this is actually 4 is equal to 6 plus c2, which means that c2 is equal to minus 2. And so the unique solution to this IVP is y of t equals 2 e to the 3t minus 2t e to the 3t. And you can verify for yourself that this thing both solves the differential equation and satisfies both of those initial conditions. Okay. All right. Let's do another case. So let's solve the IVP. That is y double prime minus 9y is equal to 0. Okay, with y of 0 being equal to 5 and y prime of 0 also being equal to 5. Okay. So again, as always, my first step here, write out the characteristic polynomial. So p of z is equal to z squared minus 9. Okay. How does this factor? Well, you could either say set this equal to 0, move 9 to the other side, and take square root, so it's plus or minus 3. Or you can notice that this is a difference of squares, so this is z minus 3, z plus 3. Okay. In which case, my roots are z is equal to 3 and minus 3. So I have two distinct real roots, right? So this immediately tells me that the general solution is y of t is equal to c1 e to the 3t plus c2 e to the minus 3t. Okay. But I was asked to actually solve the IVP, so I'm looking for a unique solution to this IVP. So what I do here is the following. So first I need to take the derivative of this thing so that I can impose the second initial condition. So the derivative of this thing is 3c1 e to the 3t minus 3c2 e to the minus 3t. All right, there's my y prime. And so imposing these two initial conditions, I have 5 is equal to y of 0, which is c1 e to the 0 plus c2 e to the 0. So that's just c1 plus c2. And then the second one is 5 is equal to y prime of 0, which is 3 c1 e to the 0 minus 3c2 e to the 0, which is 3c1 minus 3c2. Okay. So I get two equations here in two unknowns. So 5 is equal to c1 plus c2, and 5 is equal to 3c1 minus 3c2. Well, how do I solve this? One way is to look at this and say, okay, a way that I can cancel out c2 here is to multiply this first equation by 3 and add it to the second equation. So if I do that, so 3 times first equation plus second equation, so 3 times 5 is 15, 15 plus 5 is 20. So 20 is equal to 3 times c1 plus 3 times c1 is 6c1 plus 3 times c2 plus minus 3 times c2 is 0. So I get 6c1 is equal to 20, or c1 is equal to 20 over 6, right, which is 10/3, right? Okay, so c1 is 10/3. Well, once I know that c1 is 10/3, that means that c2 is 5 minus 10/3. Okay, well, 5 is how many thirds? 5 is 15/3, so this is 15/3 minus 10/3, so this is 5/3. And so the solution that I seek is y of t is 10/3 e to the 3t plus 5/3 e to the minus 3t. And if you check this, you will see not only does it solve this differential equation, it also satisfies both of these initial conditions. Okay. Let's do another example. All right, so let's solve the IVP. That is y double prime plus 9y is equal to 0, where y of 0 is equal to 5 and y prime of 0 is equal to 10. Okay. All right. So as before, what's the process here? Characteristic polynomial, right? No surprises. So characteristic polynomial for this thing is z squared plus 9. Now, you can, of course, do this via the quadratic formula, or you can just say, if I set this thing equal to 0, right, z squared plus 9 is equal to 0, then z squared is equal to minus 9. Taking the square roots of both sides, you might say, wait, I can't take the square root of a negative number. Sure you can, right? As long as you know the square root of minus 1 is I, right? Then you can freely take the square root of such things. What are my roots? Z is plus or minus 3i. Okay, so z is plus or minus 3i. So I'm in the complex root case. They always come in a conjugate pair, so if you have complex roots, then that's all you have to say. If you've done all the algebra correctly, it should be clear that you have a conjugate pair of complex roots. Okay. All right, and so what is my general solution? So my general solution is y of t is equal to c1 e to the 0t times cosine of 3t plus c2 e to the 0t times sine of 3t. So those e's don't show up if the real part of that complex number is 0. Okay. So there we go. Here's my general solution. Okay. Now I need to impose these initial conditions. So firstly, let me compute y prime. So y prime of t is minus 3c1 sine of 3t plus 3c2 cosine of 3t. Okay. So did we do that right? 3 times minus sine 3t, yep. Here, 3 times cosine 3t, yes. All right. So then, let's impose these initial conditions. 5 is equal to y of 0. Y of 0 here is c1 times cosine 0 plus c2 times sine 0. Of course, sine 0 is 0. Cosine 0 is 1. So this is just equal to c1. So c1 is 5 right off the bat. 10 is y prime of 0. Y prime of 0 is equal to minus 3c1 times sine 0 plus 3c2 times cosine 0. Sine 0 is 0, so this is actually, and cosine 0 is 1, so this is 3c2. So directly from this, I get that c1 is equal to 5, and c2 is equal to 10/3. And so our actual unique solution to this IVP here is y of t is equal to 5 cosine of 3t plus 10/3 sine of 3t. Okay. So that's how this works. So now you've seen another fully worked example for each case. Now, you might notice that as you get more and more practice at this, this is actually really quick. This is actually much quicker than solving a first order differential equation typically. Why is that? Because we've gone through all of this process in the background so that I can immediately see like how this works, because maybe I should say, rather than having a recipe for the solution like I did for a first order linear equation, that recipe relied on me having to compute some integrals, right? But in this case, I just have a bunch of canned things, like pieces, that build up my solution. Okay, now it's not true that it's actually simpler than a first order equation. And to show you why, let's try to apply this to a first order differential equation, right? So solve the IVP y prime minus 5y is equal to 0. Right? So as you notice, once I make it clear all the assumptions we're using, if I go back to the first order equation, I'll see, oh wait, this is a really simple first order equation that is basically the analog of what we're doing in the second order case. It's constant coefficient, right? So this thing is not a function of t. Typically, for a first order equation, that was a function of t. And typically for a first order equation, you didn't have a homogeneous equation, so the right-hand side was also some other function of t. And so the typical first order equation was far more general than this very special case we're doing for second order and third order. So it's not true that the orders that it's easier to write down the solution to a second order equation generally. It's just that we are in a very, very special case of constant coefficient, homogeneous, right? And of course linear, but we're always going to be in the case linear from now on, okay, until the very end of the course. So you can forget linear; they're all going to be linear. But it's constant coefficient and homogeneous that makes it easy. So you see, the second I have this written down, this is really, really easy. And for an IVP involving a single thing here, so this is, we'll say y of 0 is equal to 4. Okay, so solve this IVP. Well, let's try to do it in our new way, right? Let's write out the characteristic polynomial. What is it? Rather than being a quadratic, since this is a first order equation, the characteristic polynomial should be degree 1. It should be a linear thing, right? A degree 1 polynomial. Well, here it is. It's z minus 5. Well, what's the root? So the root is z equals 5, right? Where is z minus 5 equal to 0? Well, where z is equal to 5. Okay. Now, assuming that this recipe process works the same whenever you have distinct real roots, so in this case, the most roots we can possibly have is always 1, because this is a degree 1 polynomial. So this is it. I have distinct roots. So what is my solution? So my general solution is y of t is equal to c1, which is the only c, e to the 5t. But wait, this is exactly what we got from an equation like this, right? Y prime minus 5y equals 0, that is the same as the equation y prime is equal to 5y. This is the type of equation we did on the very first day of classes, right? So following our recipe for higher order equations, I get this is my general solution, which totally meshes with this. And of course, imposing this initial condition, right? 4 is equal to y of 0 is equal to c1 e to the 0, so that's c1. So then my solution is y of t is equal to 4 e to the 5t. Okay. So we can even use this process to solve constant coefficient linear homogeneous first order equations. It's just that those equations as first order equations are like too simple for us to care about too much, right? They're literally like some of the first things we did that weren't explicit differential equations. Okay. So that's a little showing how this stuff is backwards compatible. Okay. So then this process is pretty straightforward, right? Write out characteristic polynomial, find the roots, ask what case you're in. And the case determines a recipe. You just write out the solutions, and that's that. Okay, so then let's do some algebra review before I can say some other things that I want to say about polynomials, right? So, fact, we'll call this fact 1. Okay, a degree n polynomial has exactly n roots, counting with multiplicity. Okay, you can call this the fundamental theorem of algebra if you like. It's certainly equivalent to a statement of the fundamental theorem of algebra. This thing has exactly n roots. Remember, they could be, some of them could be complex. That's fine. Another fact, any polynomial with real coefficients let me phrase it a little differently. It's a little awkward word the way I've written it here. So let's say let P of z be a polynomial with real coefficients. Then P of z, or I should say if P of z has complex roots, all of them must occur in conjugate pairs. So if you have a root, and I'm going to, instead of using lambda and mu, I'm going to use like mu and nu. So if you have a root to your polynomial, mu plus I nu, then mu minus I nu has to also be a root. You can't just have one or the other. You have to have both. So the complex roots come in pairs. Okay. So counting with multiplicity, there's always going to be an even number of complex roots, right? Where 0 is also even, of course. So if you have 0 complex roots, that's still even, an even number of complex roots. But you're always going to have an even number of complex roots in this case. It's very important that this is only true if this has real coefficients, but that's how this works. Okay. Well, I have said counting with multiplicity here, but I haven't actually defined what multiplicity is, right? So, but if it's true that a degree n polynomial has exactly n roots, right, then I want to be able to factor this thing maximally, right? So let's suppose, suppose I have fully factored P of z. Okay. So suppose that I have fully factored P of z. So P of z is written as, say, z minus, I'll write it as z minus, like, let's write it as z minus z sub 1 to the m sub 1, z minus z sub 2 to the m sub 2, and so on, z minus z sub k to the m sub k, where the z sub I are distinct. What is this setup? What is this setup? This setup is I have fully factored P of z into this form. Forget whether or not the z sub I are each real. It will turn out, of course, since these have to come in conjugate pairs, that if any of these are complex, then there's restrictions on what can happen here. Forget about that for a second. The point is that these z sub i's are the roots of P, and I want to have combined them in such a way that each of these z sub I are distinct. So I haven't done anything, right? Like if I have a polynomial, say, that looks like this, so let's say z minus 2 times z plus 1 squared times z minus 2 cubed, right? I don't want to do anything stupid like this, right? Here, this isn't in a nice form because I have a z minus 2 factor here that hasn't been combined with this z minus 2 factor. So the reason I want these to be distinct is I want in this product to make sure that I have grouped everything already so that I've maximally grouped these things in a nice way. So here's an example. Right, this is nice, this is less nice. Okay. All right. Then, in this case, m sub I is the multiplicity sometimes called the algebraic multiplicity of z sub I as a root of P of z. Okay. We have some special names for these things. If m sub I is equal to 1, this is a root of multiplicity 1, but we say z sub I is a simple root. If m sub I is equal to 2, we say z sub I is a double root. And so on. After that, we don't really care that much. Triple root, quadruple root, we would just say it has multiplicity 3 or 4, respectively, in that case. Okay. All right. So this is what the multiplicity is. Notice a few things from this. If P of z has degree n, so if the degree of P of z is n, then I actually know what the sum of these m sub i's have to be, right? So these m sub i's have to sum to n. This is m sub k. This has to be equal to n. Okay. So these multiplicities have to sum to n. Because the highest order power showing up here is n, so z to the m sub 1 is the highest power showing up from this. If you expand this using binomial theorem, right, then you expand this, the highest power showing up is z to the m minus 1. Same thing here in all these. So the highest term showing up in this product is z to the m sub 1 times z to the m sub 2 times z to the m sub k. Combining all those terms means adding the exponents, so those exponents have to sum to n. So all these multiplicities added up together have to sum to n. It's another way of kind of trying to keep track of the thing you're doing. I'll give you some examples next time so we can move on to what this means more generally. Okay, before we can get into the topic of non-homogeneous, it makes sense to really understand how this homogeneous case generalizes to higher order things and how this recipe works when we have higher order equations. So that's what we'll do tomorrow. So I will see you all then.